There are places in the cosmos where gravity is so strong not even light can escape. Black holes. They're the universe's ultimate mystery boxes born from the collapse of massive stars. Once just a ghost in Einstein's equations, we now know black holes are real. They lurk in the centers of galaxies, including our own Milky Way, challenging our understanding of space and time. The allure of a black hole lies in its unseen power, a singularity cloaked by the event horizon. Crossing this boundary is a one-way trip. What lies beyond remains forever hidden. This profound unknown fuels our imagination and scientific drive. Black holes are not just objects, they're laboratories for testing the limits of physics. We can't see them directly, but we hunt for their influence. Stars orbiting invisible companions, or the brilliant light of matter spiraling into the abyss. Each observation adds a brushstroke to our portrait of these enigmatic objects. Black holes play a crucial role in the evolution of galaxies, regulating star formation and spewing out powerful jets of energy. By studying them, we learn about the life and death of stars, the formation of galaxies, and the dance of matter and energy across space-time. In their darkness, we find a light that illuminates the grand story of the cosmos. Our journey to understand these cosmic titans is about more than curiosity. It's about uncovering the forces that shape the universe. Black holes influence the very structure of the cosmos on the largest scales. Through them, we glimpse the boundaries of our knowledge. In the shadow of a black hole, we find the light of discovery. 55 million light-years away lies Messier 87, or M87, a giant elliptical galaxy with a monstrous heart. At its center is a supermassive black hole, 6.5 billion times the mass of our Sun. This behemoth anchors the entire galaxy, its gravity almost beyond comprehension. It's not quiet, an active black hole feeding on a swirling disk of gas and dust. As matter spirals in, it heats up and glows, but right at the edge, space-time plunges into darkness. The black hole's shadow. This shadow isn't like a tree's, it's the visual footprint of the event horizon, silhouetted against the glowing matter. The edge is a place of extreme physics. Light itself can orbit the black hole, creating a thin, bright photon ring. Observing this shadow lets us test Einstein's theory in the most extreme environment imaginable. In 2019, the Event Horizon Telescope captured the first direct image of M87's black hole, a fuzzy orange donut of light around a perfect circle of black. That image was a monumental achievement, but it was just a snapshot. What happens before and after? How does the shadow and its ring change over time? To answer that, we needed more than a picture. We needed a virtual universe. Scientists set out to build a digital model, letting us watch the black hole's environment evolve. This virtual approach opens a new window into the heart of M87. The shadow's edge is where theory meets observation. By simulating this region, we can explore the unseeable. The journey from image to simulation is the next step in unraveling the black hole's secrets. To study a black hole 55 million light-years away, scientists built a digital twin using supercomputers. The Frontera machine at the Texas Advanced Computing Center simulated the chaotic environment at M87's edge, tracking plasma, magnetic fields, and photons. This virtual lab let researchers fly to the event horizon, zoom in on the photon ring, and watch the black hole's environment evolve. The simulation bridged theory and observation, producing a dynamic living system instead of a static image. Millions of hours of processing yielded the most detailed look ever at a black hole's shadow realm. By comparing simulation results to the Event Horizon Telescope's image, scientists could test and refine their models. This is the heart of the scientific method, now applied to the universe's most extreme objects. The simulation of M87's black hole revealed three key discoveries. First, electrons in the plasma are much colder than protons, a crucial clue about how energy moves in this violent environment. Second, the black hole's shadow is stable, but the bright photon ring flickers and wobbles as turbulent blobs of plasma orbit the black hole. This means the ring is dynamic, not static, a shimmering light show powered by gravity and magnetism. Third, magnetic fields play a critical role, sometimes pushing back against gravity and launching colossal jets of matter into space. These findings connect the small-scale physics near the event horizon to the black hole's impact on its entire galaxy. Each discovery challenges our assumptions and points to deeper questions. Simulation is now a driver of discovery, not just confirmation. Let's dive into the temperature gap. Plasma, the fourth state of matter, dominates the universe, including the disk around M87's black hole. In this extreme environment, gravity and magnetic fields whip the plasma into chaos. The simulation showed that protons, being heavier, absorb most of the turbulent energy, reaching billions of degrees. Electrons, much lighter, stay significantly cooler. This matters because electrons produce the light we see. Knowing their temperature helps us interpret black hole images. The simulation naturally produced this two-temperature plasma, refining our understanding of how black holes feed and shine. It's a leap from black and white to full color in our models. To truly understand black hole light, we must account for this complex thermal dynamic. The simulation revealed the hidden thermal dance at the edge of oblivion. The bright ring in the M87 image is the photon ring, a path where light orbits the black hole. The simulation revealed this ring isn't static. It flickers and shimmers as clumps of hot plasma orbit nearby. These bright spots illuminate the ring from different angles, causing its brightness to vary. This flickering encodes information about the black hole's mass and spin. By studying these light patterns, we can measure fundamental black hole properties with new precision. The simulation acts as a Rosetta Stone, translating flickers into physical parameters. It predicts that the shadow remains stable, but the light around it dances. This is a testable hypothesis for future Event Horizon Telescope observations. If we see this variability, it will confirm our models and open a new window into black hole physics. The image is just the first frame. The simulation predicts the movie. The photon ring's dance is a cosmic signature waiting to be observed. Each flicker is a clue to the black hole's secrets. The next step, watch the light move in real time. Gravity isn't the only force at play. Magnetic fields are co-stars in the black hole's drama. Generated by swirling plasma, these fields guide and constrain matter, storing immense energy. The simulation showed magnetic pressure can rival gravity, sometimes pushing plasma away instead of letting it fall in. This magnetic pushback is key to launching the black hole's spectacular jets. Beams of matter ejected at nearly light speed. Twisted magnetic fields act as a cosmic slingshot, flinging plasma outwards. This links the smallest scales near the event horizon to the galaxy's largest structures. The jets inject energy into the galaxy, shaping its evolution. The simulation reveals the engine behind these cosmic fireworks. To simulate a black hole, scientists use GRMHD, General Relativistic Magnetohydrodynamics. This framework combines Einstein's relativity with the physics of magnetized plasma. The simulation divides space into millions of cells, solving complex equations for each one at every moment. Then, radiative transfer techniques calculate how light travels from the plasma to a virtual camera, bending around the black hole. This two-step process turns raw data into images we can compare with real observations. GRMHD is the most complete physical description we have for these environments. It's like directing a movie with the universe's own rulebook. This approach bridges theory and observation, letting us see the unseeable. The 2019 image of M87's black hole was just the beginning. The new simulation predicts the flickering and wobbling of the photon ring. The next challenge is to capture this motion. The goal, create the first movie of a black hole shadow evolving in real time. This will require sharper images, more telescopes, and even more powerful simulations. By tracking the motion of bright spots, we can map spacetime and test Einstein's theory to its limits. Any deviation could hint at new physics beyond relativity. Our quest to understand black holes pushes the boundaries of knowledge. From a single image to a dynamic movie, we're peeling back the layers of the universe's greatest mystery. Each step brings us closer to the fundamental laws that govern existence. The journey into the shadow realm has just begun.